Okay, hello everyone. I just wanted to talk a little bit about specific heat capacity and how to calculate problems and how to solve for energy absorbed or released by a substance. So first of all, I want to start with this little scenario up here. It says, why does the concrete get so hot so fast and the water doesn't? They are exposed to the sun for the same amount of time because they each have a different specific heat capacity. So first of all, if you think back to the summertime, and if you're walking along the concrete without any flip-flops on, the concrete is very hot and you're rushing to get yourself into the water because the water is very cool. Well, it doesn't make much sense because they're sitting out in the heat for the same amount of time. So concrete gets a lot hotter in the same amount of time that the water is sitting out there. So concrete gets a lot warmer and the water stays cool. And that's because they absorb heat and store heat at different rates. And we call this specific heat capacity and is represented with a little kind of italicized C. So by definition, the specific heat capacity of a substance is the amount of heat energy needed to raise the temperature of 1 gram of a material or substance by 1 degree Celsius. So let me give you an idea what we're talking about here. So the specific heat capacity of water is 4.186 joules per grams times degrees Celsius. So that means it takes 4.18 joules of energy to raise 1 gram of water 1 degree Celsius. Compared to the specific heat of concrete, which is 0.880 joules per grams times degrees Celsius. So this means that concrete, it takes only, not even 1 joule of energy, it takes less than 1 joule of energy to raise 1 gram of concrete 1 degree Celsius. So that means it takes a lot less energy, okay, for the concrete. It takes a lot less energy to get that concrete to raise 1 gram by 1 degree Celsius. So think of it this way. Water can pack in 4.186 joules of energy, okay, into its molecules before the temperature increases. Concrete, however, can only pack in 0.880 joules of energy before the temperature goes up by 1 degree. So concrete gets warmer a lot faster because it can't absorb that much heat energy before the temperature goes up. Let me show you this chart. So this is called a specific heat chart, and it's not super comprehensive, but it gives you different substances and their different specific heats. Water has one of the highest specific heats, and that has to do with its hydrogen bonds. So water can pack in and absorb a whole lot of heat energy before the temperature will go up by 1 degree. So aluminum has a specific heat of 0.900 joules per grams times degrees Celsius. So that's almost the same amount of concrete. Iron, 0.449. So that means it cannot absorb that much heat energy, and then the temperature will go up. Silver, even less, 0.235 joules per grams times degrees Celsius, and so on and so forth. Gold, super low specific heat. So that means gold can absorb very little amount of heat energy before the temperature goes up. Now, as you notice, aluminum, iron, silver, gold, they all have very low specific heats, and that's because they're metals. So metals are considered to be conductors, and they let heat pass through them very, very quickly. So all our metals are going to have low specific heats because they're good conductors. They're not going to absorb a lot of heat energy. It's going to let that heat energy pass through it, and the temperature is going to go up quickly. So let's look at our equation. So our equation, Q, is energy absorbed or released. So if we're solving for energy absorbed or released, we're going to solve for Q. Info we need the mass of our substance in grams. We need the change in temperature. So change in temperature is final temperature minus initial temperature. And that's what's going to go right here. Delta means change in. And then you also need the specific heat of a substance. It says page 476. Don't worry about that. I will give you this chart, and that's all you will need. Okay, so let's do a few practice problems. Let's see how this works. So number one, it says how much heat energy is absorbed. Okay, so we're looking at absorbing heat energy. So we are solving for Q. So how much heat energy is absorbed by 750 gram iron skillet when its temperature raises from 25 degrees Celsius to 125 degrees Celsius. So we're solving for Q, mass times delta T times specific heat. So the mass of my substance is 750 grams. Change in temperature, this is my final temperature, this is my initial temperature. So I'm going to do 125 minus 25. So my delta T is going to be 100 degrees Celsius. Now what I have to do is I have to go to my chart, see how it says iron. This is a substance we're dealing with. So different substances absorb and release heat energy at different rates. So I need to find iron. Iron has a specific heat of 0.449 joules per grams times degrees Celsius. So I'm going to go back here and I'm going to plug in for C 0.449 joules per grams times degrees Celsius. So joules cancel out, grams cancels out, degrees Celsius cancels out. So I'm going to multiply straight across. 750 times 100 times 0.449 is going to give me 33,675 joules of energy. So our iron skillet, when the temperature goes up by 100 degrees, is going to absorb 33,675 joules of energy. Okay, so let's do number two. I'll do it in a different color here. Do it in blue. Okay, it says how much heat energy is lost. So we're solving for Q again by 1,200 grams of silver if it is cooled from 35 degrees Celsius to 21 degrees Celsius. So we're still going to use Q. The fact that our heat energy is being lost means we're going to have a negative value in our answer, which is fine. So again, we're going to use Q is equal to M times change in temperature times specific heat. So Q is equal to, the mass of my silver is 1,200 grams. So I have to calculate my change in temperature. So change in temperature. My final temperature is 21 degrees minus my initial temperature, which is 35. So 21 minus 35 is equal to negative 14 degrees. That's my change in temperature. Now I've got to go to my chart. I have to find the specific heat of silver. So specific heat of silver is 0.235. So I'm going to plug that in, 0.235 joules per grams times degrees Celsius. Grams cancel out. Whoops, this was my degrees Celsius, cancel out. I'm going to multiply straight across. So 1,200 times negative 14 times 0.235 is equal to negative 3,948 joules of energy. So this silver is losing, okay, it's releasing heat energy into the atmosphere. And we know it's being released because that is a negative value. Okay, let's do another problem. Okay, so these problems, we are solving for specific heat. So the specific, we're going to use the same equation. I'm going to give myself another slide here. I got 5 minutes to get this done. Duplicate. Okay, I'm just going to use this as a blank slide. Okay, so I'm going to start with my original equation. Q is equal to M times change in temperature times specific heat. So the problems we're going to solve on this page is we are calculating for specific heat. So let's go back here. I'm going to rearrange my equation. I want to solve for C. So I'm going to divide by M times change in temperature. What I do to one side of the equation, I have to do the other. So my new equation, specific heat, is Q divided by M times delta T. So that's what I'm going to use for these. Specific heat is lowercase c, so I'm going to use C is equal to Q divided by M times change in temperature. Okay, so it says if a 10-gram piece of metal absorbs 297 joules of energy when the temperature increases from 22 degrees to 55, what is the specific heat and what is the metal? So we're going to use this equation right here. C is equal to, this is energy, that's Q, 297 joules, divided by the mass, which is 10 grams. And then we have to multiply the change in temperature. So 55 is my final temperature, minus 22 is my initial. So my change in temperature is 33 degrees. 33 degrees Celsius. Now I'm going to do my math. I'm going to say 297 divided by, I like to put the stuff on the bottom in parentheses, so parentheses, 10 times 33, close parentheses, is equal to 0.90 joules per grams times degrees Celsius. So that's my specific heat. So it says, what is the metal? So I'm going to go back to my chart, and the metal that I'm dealing with is aluminum. Aluminum. Okay, so let's do our last problem, number 2. It says if it takes 41 joules to heat a piece of metal with a mass of 18.69 grams from 10 degrees to 27 degrees, what is the specific heat of the metal and what is the metal? So again, we're going to use this equation. So we're going to solve for C. Let's see if I can squeeze it down here. C is equal to 41 joules of energy divided by my mass, which is 18.69, times it by my change in temperature. So 27 minus 10 is 17 degrees, equals to, so 41 divided by, I'm going to do parentheses, 18.69 times 17, close parentheses, is equal to 0.129. I'm going to put all these units together, joules per grams times degrees Celsius. I'm going to go back to my chart, and 0.129. So my metal in this case is gold. Okay, just in the nick of time. Hopefully that helps with your assignment that you're about to do, and have a great day.